in this presentation, I will try to focus on the A-PHY portion of the mass framework that was described in details in the previous presentation by James, Ariel, and Hero. So let me start. So this is an overview of the situation and the development of the and progress of the market as we foresee it in MIPI Alliance. Currently, there are proprietary SerDes solutions supporting the required long-reach capabilities by bridges, and having a market with the proprietary solutions is not it's not a good situation in a market that is ramping up and requires a lot of support. So standardized solution will enable cost reduction via economy of scale and will ensure the interoperability between vendors and allowing flexibility for the OEM tier ones. And this is what we show here when we start with the A-PHY standard. And this is the first A-PHY bridges that will be available shortly by the end of the year. And going forward, there is also even better improvement by having the A-PHY integrated into the sensors and in the future into the actual SoCs in order to lower the cost and deboom by utilizing the A-PHY, which has native interfaces to the MIPI protocols. So that's a natural development of the market to reduce the overall reduce the overall cost and allow multiple vendors to support the OEM and tier ones. So what is the A-PHY standard? A-PHY is a MIPI Automotive long-reach PHY. It's the first standard, industry standard for long-reach asymmetric SerDes solution that is targeted for both ADAS and ADS surround sensors applications and infotainment systems. It offers a direct coupling to the native CSI, DSI from MIPI and the DP and EDP from VISA after working with a liaison between the two organizations. It brings high performance of up to 16 gigabit per second for cables up to 15 meters and provides high noise immunity while having ultra low packet error rate of 10 by minus 19. It supports both bridge-based systems and integrated endpoints, and there is an interoperability that's maintained between them, so it could work with both bridges and integrated solutions. It supports, of course, both coax and shielded, twisted or shielded parallel pairs, and it supports also delivering the power over cable in order to reduce the cabling needed for connecting end unit like a camera sensor. There is already an enhancement to the A-PHY, the A-PHY 1.1, which is going to be finalized by the end of the year. This is spec ready, mainly under final reviews. And in this version, we increased the support for lower cost legacy cables. We doubled the uplink data rate, and we added a star quad cable support to enable dual downlink operation, bringing the maximum downlink bandwidth to 32 gigabit per second. The A-PHY version 1.0 has the performance and immunity-based profiles. What it means? It means that there is an ability to support the variant requirements or variety of requirements made by different OEMs and tier ones that have very different market segments that need to be supported. So if I can scale up the bandwidth and continue supporting the same frequencies and same modulation bandwidth without changing cable and connectors definitions by increasing the PAM level of the modulation scheme. It has support for the different OEM and their different requirements by enabling two profiles. This was done after a very long EMC tests. The MIPI as an organization ran an independent lab to evaluate noise levels and shielding effects degradation after mechanical stress and aging. So based on this testing and multiple requirements coming from the OEM, there were defined two performance and noise immunity profiles. Profile 1, which is optimized for low power implementations, and it's focused on the lower gears and providing noise immunity or lower noise immunity and the packet error rate target of 10 by -9. And the second profile, profile 2, is optimized for the lifespan of the vehicle with a robust link for all gears from 1 to 5, supporting high noise immunity, very high levels of NBI, and still maintaining packet error rate of 10 by -19. Interoperability is a very important aspect going forward. So these solutions of A-PHY are full interoperable, and also interoperable between the gears. So it means that if there is a device that supports gear 5, it will also be required to support gear 4, 3, 2, and 1. All the lower gears will be supported. In the right table, you can see that there are 5 gears for downlink, between 2 gigabit per second and up to 16 gigabit per second. And by utilizing different PAM modulation and NRZ modulation, the bandwidth of the signals will not cross the 2 gigahertz, which enables very clear or very simplified cables with clear channel definitions for these kind of frequencies, also from insertion loss, return loss, and other channel aspects. You get a 90% data, net application data rate, so very low overhead for the system. The uplink has 100 megabit per second, working in NRZ 8-bit, 10-bit, which provides 55 megabit per second net data rate. So what makes the A-PHY so robust and efficient? So the A-PHY brings a new approach that is focused on being able to accommodate the different noise profiles and different noise attacks that are possible in an automotive market. The main thing is to have retransmission and narrowband cancellation, narrowband interference cancellation, which is a mechanism that is residing inside the PHY level, which means that this is a fully transparent mechanism to the upper layers. It has a predefined overall delay of up to 6 microseconds, for example, for 16 gigahertz link. And when I say overall, it means between the link layer or the entrance to the link layer to the exit of the link layer from the transmitter to the receiver. All of this will have a predefined delay of 6 micro, which is happening only between the two PHYs, and it's not being aggregated if there is a daisy chain, for example. So it's time bounded, local PHY level retransmission. It means only in this area there is a possibility for retransmission, and it is predefined to have an overall delay of no more than, for example, 6 microseconds. There is a dynamic modulation for the retransmitted packets. So to get better error resistance, what it means is that once you work, for example, in PAM16 for gear 5 or PAM4 for gear 3, so when there is an error and there is a need for retransmission, the retransmitted packet will be sent in a lower modulation. Let's say instead of PAM4, it will be sent in PAM2. This mechanism is adding much more resistance to the noise and making sure that this packet will be transmitted safely to the other side. And detailed explanation of this mechanism is available in the MIPI specification and in multiple documents that are available in the MIPI repository. It is highly resilient. It can overcome large thousands of symbol long error bursts, and it has multiple tens of millivolts for instantly attacking NBI peaks. So it's being able to support this with this mechanism that some other mechanism, which are more traditional, are not accustomed, cannot accommodate. So it enables to do highly reliable transmission of packet error rate of 10 to the minus 19 by still maintaining very low overhead of 90% net data rate. The A packet structure is relatively simple. It carries the native protocol data and all the information that the A-PHY data link layer requires in order to perform its functions efficiently. The downlink and the uplink has the same packet structure for simplicity. The structure is optimized for supporting aggregation of multiple protocols with minimal overhead and latency. A packet header contains all required information as quality of service, priority, destination, and protocol type. And the structure is having header of 8 bytes, including message counter, a payload, and a tail of 4 bytes, which is a CRC32. The A-PHY Interconnect is as seen here. It is a single lane point-to-point serial communication technology. It has support for multiple cable type like SDP and coax. It supports power over cable, and it supports up to 15 meter with 4 inline connectors. A-PHY supports functional safety, and it has packets are end-to-end protected as recommended by the ISO 26262 with CRC32 for each packet, providing homing distance of more than 3, a message counter of 8-bit wide, and there is a mechanism for timeout monitoring to have a keep alive functions. These are measures that are necessary to argue high diagnostic coverage for communication bus by the ISO 26262, and all other higher level functional safety features that are necessary to fulfill the required system level ASIL definition are expected to be managed by upper layers, and specifically in MIPI, you have heard about the CSC for camera as an example of implementation such higher layer solution. In general, A-PHY tunnels end-to-end all the protection elements allowing both safety and security. And as James mentioned there earlier, the security will be covered by Rick in the coming presentations. So what is coming for A-PHY 1.1? A-PHY 1.1 enhancement include doubling the data rate of the uplink to 200 megabits per second, resulting in 125 megabits net data rate, and maintaining the same modulation bandwidth. This is in a similar way to maintain the different levels of system and to maintain low probability of errors. There is additional optional PAM4 modes for Gear 1 and Gear 2. So supporting, again, lower modulation bandwidth, which allows for, again, simpler cables and making the overall end-to-end solution is simpler and with better cost. And addition of STQ cables, the support, which I will describe in the next slide. The enhanced performance and variance and scalability, the expanding the PAM4 encoding to the lower gears reduce the operating signal rate in these gears, allowing implementation, as I mentioned earlier, lower cost legacy cables and connectors. Nonetheless, it has the same high noise immunity and supporting the same high noise immunity with an ultra low packet error rate of 10 by minus 19 for the vehicle lifespan. From interoperability and compatibility, as mentioned previously, this is a major item here. So A-PHY 1.1 is backward compatible with 1.0, and A-PHY 1.0 is forward compatible with 1.1. And A-PHY guarantees full interprofile interoperability. Device will support all the various gears below them, as mentioned previously. This has not changed in the A-PHY 1.1. So now it's also applicable to the uplink and not just the downlink, because we have two gears in the uplink. So what is the added support for STQ cable? So STQ is a Starquad shielded dual differential pair. We have two pairs inside one shielded cable. So it's in comparison to two STP cables or SDP cables. This is better size and cost and weight for driving such a high-speed data. And there are three modes that this can work over STQ cable. So the first one is the dual downlink configuration. And in the dual downlink configuration, there is a possibility to work on the two pairs going in the downlink direction with up to 16 gigabit per second for each of them. So it means you can get up to 32 gigabit per second for the downlink. The uplink will be available only on the pair 0, what is configured as pair 0. And there you could have either 100 or 200 megabits per second uplink. The second configuration is asymmetric configuration, which means that in the one pair, you can have a downlink of up to 16 gigabit per second. And in the reverse downlink, which is not uplink, but a reverse downlink, it's the same configuration or PHY definition as the downlink, but on the other direction. So we distinguish it from the original uplink by calling it reverse downlink to have up to 4 gigabit per second. It means that on this downlink you can have gear 3 to gear 5, and in this uplink you could, or reverse downlink, sorry, you could have 2 or 4 gigabit per second in order to have flexibility. The third mode of this STQ cable is actually having a symmetric configuration, which means that you have the same bandwidth on the downlink and the reverse downlink. So it enables either 8, 12, or 16 gigabit per second in each direction. A-PHY is the foundation of the MIPI Automotive SerDes solution, as was detailedly described in the previous presentation. There is a direct coupling of the MIPI native protocols to the A-PHY, and it has end-to-end functional safety, this end-to-end security, which is work in progress, and multiple supporting interface like I2C, GPIO, Ethernet, and now being under design or definitions, the MIPI I3C and SPI. Both are expected to be available early next year. So just one example, there is already a MIPI A-PHY version 1.1 compliant system with up to 8 gigabit. It's supporting Gear 1 to Gear 3 with the support of ISO 26262.
Here we have a demonstration of the first A-PHY based system. You can see on this side that we have a standard on-semi sensor AR820, which is connected to Valence EVB, including the 7031, which is the A-PHY based transmitter supporting up to 8 gigabit per second. This is connected via a standard automotive connector through a Dakar 462 coax cable with 4-in-line connector for 50 meters until it reaches the ECU side, which has a 7044, which is Valence quad receiver, which has 4 A-PHY ports supporting 8 gigabit per second. From here you can see the live stream coming from the ECU to the display. So we have the first actual chipset available for A-PHY standard, supporting up to 8 gigabit per second, and samples will be available by the end of the year for customers.
So few example use case for the A-PHY that were used as part of the development. So one of these use cases is the surround view. So there are multiple items that relate to that. First, as you said, there is a high performance up to 16 gigabit per second of up to 15 meters. So there is no limitation on the location of the device, and still maintaining the ultra low packet error rate with high noise immunity. So there is freedom to locate your devices anywhere in the car, even if it's a bigger car. And the second thing is that there is a backward and forward compatibility. So easy installation, easy maintenance, as it's self-adapting, and also being able to support the different type of gears and the different configuration, either it's integrated or bridge devices. And The third thing is that there is a direct coupling to the CSI2, for example, in this surround view case, and the control interfaces. So it's easy to do, and it's possible to do an integration of the A-PHY into the device. So cost and power reduction are available for the overall solution with support of up to 6 watt delivery to the end unit. So that's a, a unique and a strong point of being able to integrate the A-PHY into the endpoint devices. A second use case is the use case of the display cockpit. And here, the bandwidth of the A-PHY and the capability to support multiple use cases, multiple architectures, all the new and advanced architecture, and being able to aggregate and daisy chain the A-PHY packets. So this is a general description, and these kind of numbers are available today in different use cases, reaching very high bandwidth. So, for example, if you need to support these daisy chain capabilities, you reach very or such a long daisy chain, you get the same requirements for high speed, and with the support of A-PHY high packet error rate, there is a capability or ability to utilize the VISA DSC compression of up to 1 to 3. So can be applied with no additional overhead. There is no, because of the high immunity and the low packet error rate, the addition of compression does not impact the required overhead. So link can be supported in 16 gigabits. A link can support up to 48 gigabit per second and 43 gigabit per second net data rate. And when going and utilizing A-PHY 1.1 dual downlink of 32 gigabit per second, supporting compression, there is a capability of reaching 96 gigabit per second per link. And that's about 86 gigabit per second net data. So that's a capability. And also when looking at the capabilities of the return channel flexibility, it allows the designer of the specific vehicle to utilize multiple configurations and being able to upgrade some of the components without any dependencies on the different modules. So again, just to emphasize the elements in this use case. So for example, for the infotainment cluster, the daisy support of the daisy chain, ultra low packet enable the use of compression with no additional overhead, the high bandwidth of 16 gigabit per second and higher when implementing compression allows very flexible and very high bandwidth capabilities for displays. The support for the rear seat allows for the capability of reaching up to 15 meters, allows for flexibility and freedom to locate it where the ECU and the displays in any specific location. It allows support for both DSI2 and DisplayPort, and it also has HDCP support. And of course, for the instrument cluster, the functional safety and the ultra low packet error rate are very important. So to summarize, the MIPI A-PHY and the MIPI organization brings an established ecosystem with multiple vendors working on A-PHY compliant chipsets. And as mentioned, first samples will be available by the end of the year. There is a clear and forward-looking roadmap and planning. A-PHY 1.0 was released in 2022. A-PHY 1.1 is targeted to be released by the end of the year, and A-PHY v.2 is now starting work within the A-PHY working group, and any contributing company is welcome to join and provide feedback, as the work already started and is being ramped up this coming months. There are new protocol adaptation layer, PALs. So there is always an expanding support for more and more interfaces such as SPI and Ethernet and I3C. And we have also forward-looking in the plan more adaptation layer to develop based on market inputs and contributing member inputs. There is a support for multiple advanced use cases with clear advantages of an industry standard. We have an error-free links, a seamless integration, and interoperability and forward compatibility, which is a trademark of MIPI Alliance in all its products. So for more automotive resources, there is the A-PHY specification homepage and the MIPI white papers of introduction to MAS. It can all be found in the links there and in the MIPI website. Q&A.
Ido, thank you very much. Great job. Here's a question that came in very early on for you. Do you have a plan for optical interface solutions instead of copper medium in the future?
So this topic did not rise at this point. We feel, at least at the coming, at least not for 2.0, there's still no discussion about optical, but the group will be open to any such a proposal based on technical merits to support. But currently, the technical perspective, it seems that we can reach higher speeds with the same capabilities still on copper cabling, and we feel that from development, as long as we can keep the copper, this is still will be the main direction.
And to follow on to that, my understanding, especially in automotive, the preference is to stay with a medium that's less expensive, and optical may be quite expensive for the automobile at this time. I
agree, but I was trying to refrain from going into cost aspects. In the work group, we are looking mainly on technical aspects.
Okay.
And as I said, if there is a proposal and technical justification from different aspects like immunity, like capability to go to longer distances or whatever, I'm sure the group will consider that.
Okay. Here's another question. How easy is it to migrate from legacy SerDes to an A-PHY?
I would say that, at least from the experience that we have until now, it should be very easy. I think that the migration to the A-PHY based systems, while giving more standardized solution, it also enables easier maintenance as it's adaptive, and it's not it does not require any fine tuning for each design, but allows you to work on any channel that meets the A-PHY channel. The system will adapt itself to fit the best performance at these conditions. So one of the goals of A-PHY was to generate a solution that is easily installed and easily maintenance over the life cycle of the vehicle.
Thank you. We have a question about errors as well. How did you arrive at the PER of 10 to the minus 19?
So that's a very good question. And for that, I would require more detailed and low-level explanation. I could actually, it could be a complete session, a separate session. I would say that if anyone would like to get the details of this calculation, there are resources within the MIPI repository, and I'd be happy to share these allocations to any contributing members and give some more background after sharing this. But if the question is coming from a non-MIPI member, I think we can have a separate session to discuss this and to provide a more detailed answer. But I'm sorry, but it's not something that I can do in a very short.
Yeah, I am sure it's detailed and not something that can be done in 30 seconds. Here's a simple one for you then.
Okay.
Does MIPI provide a channel model for A-PHY?
So MIPI has a channel model. It has a noise model. Everything is available. I think, again, this is available for all contributing members. And Raj, who is also the co-chair of the A-PHY working group, will discuss exactly these topics in the next session about simulation. Any member can get an access to a simulation environment that can provide him all the necessary information on the channel and the noise configuration and everything.
Okay.
Okay.
And then we have another one here that says, what is the reason behind using 8B, 10B encoding instead of 64, 66 or higher versions? And I guess the question is brought up because of the concern of degradation or overhead.
So, as mentioned, the 10-bit, the 8-bit, 10-bit, especially when looking at the lower gears, it provides a very simple and forward, easy to implement solution that enables, due to the structure of the 8-bit, 10-bit, a relatively simple implementation on both sides and still maintain a reasonable net data rate. So again, these are topics that were discussed heavily within the group, and simulations and analysis were done by multiple companies. So again, if someone would like to get a more detailed explanation, I'd be happy to do that as part of the group discussions and refer them to the right presentation in the group repository.
Okay. Now, one last question for you, though, just to close out our time, is we all know how important interoperability is. Is MIPI planning to do anything to ensure interoperability with A-PHY?
So, of course, as I mentioned multiple times during the presentation, we see interoperability as an important and differentiator for a standard solution. So yes, MIPI, as in the group activity, there is a strong emphasis on interoperability, and in the testing documentation that the group will provide and working on right now, interoperability between devices, between different vendor devices, between different type of devices like bridges and integrated devices are all considered and should be supported by this documentation.
Well, that's all the time we have now. Ido, I'd like to just thank you again for your presentation on talking about A-PHY and how to make it simple.